Hey everyone, we are going to start with our course Deep Learning with this video. I will talk about why do we move towards deep learning after we have learned so much in the area of classical statistical models and machine learning models. We'll talk about limitations of traditional ML models. We will talk about some fun use cases which essentially will tell you what are the possibilities which we can start to address with deep learning models. We'll give you a brief overview of the deep learning algorithms that we will be focusing on in this course, and we'll talk about what all tools people generally use and what will be our focus in the course. Okay. So let's start with the limitations of traditional ML model. The first limitation that you should realize by now is that although machine learning models are very good, for example, XGBoost is widely used across industries. What happens though is these algorithms perform very well given a small data size or medium sized data size. But these days the data is available in huge quantities. It keeps on piling up. The huge amount of information that we are continuously gathering. Traditional machine learning algorithms are not able to take benefit of that additional information. Beyond a certain size of data, the performance of the algorithm kind of flattens out. It doesn't keep on improving as it does when initially the data size is increasing. So this saturation is something which essentially hinders our usage of the information which is available. It kind of starts to go to waste. And that is where deep learning or medium-sized neural networks enter. They can make use of this continuous piling up a huge amount of information and give you even better results. They can push for that final improvement which we were not able to achieve with traditional ML algorithm, which might not sound very big, but when we are talking about delivering life-saving applications, delivering very critical applications where even a small amount of error is not something that we will accept, these become important. There is another thing. The machine learning algorithm that we have been working with, as you saw in the last course, they were all working with tabular format of data, or essentially needed that the data needs to be converted to a tabular format. Now, the kind of data which AI deals with, or the kind of inputs which AI takes, it can be text, or it can be videos, it can be images, it can be audio. These are not inherently tabular format data. Of course, they can be used as tabular format data. For example, each pixel in an image can be considered a variable, a column. And if we are looking at, say, 30 cross 30 image, we are essentially looking at 900 columns. But the moment we start to treat each pixel as a separate variable, we are essentially letting go of the information inherent in the structure of the image. The first pixel at the left corner and the last pixel which is at the right corner, down corner, are not very near to each other. The first and second pixel are very near to each other, and that nearness is again an information which we are essentially losing the moment we start working with an image as a tabular data. So the structure information is something that we are not making use of if we go with traditional modeling algorithm. There can be, of course, hackish way to include that information in the data, but that becomes very big hassle pretty soon. Another example is sequential data, text data or audio data, where we saw in our text mining processes that we can convert text to features or tabular data by creating bag of words features or TF-IDF features. But again, these feature or these columnar representation of text data are not making use of spatial information. In a sentence, how far away two particular words are, that information is not being made use of. All that we are looking at how often a word appears and so on, maybe normalized frequencies, but we don't go beyond that. And that is something deep learning architectures can make use of. There is one more thing, that with unstructured data, feature space is very high dimensional. We saw in text data also that easily very small number of observations can lead to have thousands of bag of words features, and that becomes even a bigger problem to solve as in when we start to consider the sequence of things as well. Okay, now when very high dimensional space, one thing that happens is simple idea which essentially drives many of the machine learning algorithm that we have gone through. The partition of feature space doesn't work very well. It works for a good enough number of problems, but when the problem structure or relationship between the outcome and the incoming data is very, very complex, then simple partition of feature space is not something which gives very good results, or I shouldn't say good results at this point. Maybe you can build models which give you 92% accuracy, but that's not cutting edge. When I say good results in this context, essentially means we are trying to push the accuracy to 95% or 99% or even 99.9%. Okay, and that is where what again differentiate these two different techniques, machine learning and deep learning, is deep learning focuses on functional approximation rather than trying to come up with a hackish way to model the function by partitioning the feature space. Okay, so we will look at some use cases, and as I said, the way I've picked up these use cases are by the fun quotient rather than how critical these are in an industry. I just wanted to show you that with deep learning how close we come to the task that we like to term as AI. See here, in this example, you will see, just look at the video for a moment.
It's been less than a week since the deadliest mass shooting in American history.
Our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
If you missed it, essentially here what this particular application is doing is making Obama speak, or rather in more plain terms, it's overlapping the audio over a video, and it's very difficult to differentiate between the real and the fabricated video.
I visited with the families of many of the victims on Thursday.
Target videos. Note that all four are synthetic and have different lighting conditions.
To help families refinance their homes, to invest in things like high-tech.
And it doesn't end there. There are tons of different use cases. Look at this, where deep learning can be used to caption image like that, and in such a detailed fashion. Look at the image on the right hand side. There is such in a very small image, the deep learning algorithms are able to extract so many annotations associated with this image. Elephant is standing, elephant is brown, this is a roof of a building, there is a football, there is a leg of an elephant, man is wearing red color t-shirt, and so on. Now this is important, or rather this is a massive achievement from the perspective of computer vision. Again, very one of the very crucial inputs to any AI task. Whereas from as a human user, it's impossible for us to focus on every aspect of image. It is impossible for us to perform very well irrespective of how well the lighting techniques is, how distracted we are, and so on. AI doesn't have all these problems. It becomes important from the perspective of processing an image input. It could be security, it could be assessing how happy people are in your store, it could be searching for ships in ocean, it could be looking at how forests are increasing in size or decreasing in size. It could be n number of tasks which we can achieve to do this, which we can achieve by making use of these kind of techniques. Here's another interesting use case, where the input are the blurred or very reduced in quality images which you can see on the left hand side. The ground truth or the real images which were blurred to make the left hand side input are on the rightmost. Using deep learning techniques, these blurred images have been restored nearly identical to what the reality was. There are tons of use cases for this. We can work with compressed data and still get back by using deep learning technique, get back the enhanced data. We can, if anybody recalls, the blurred CCTV images. CCTV cameras are not very high quality yet, and many a times the faces are not clear or the number plates of vehicles are not clear. We can use these techniques to enhance those images and catch the perpetrators. This is a fun use case or fun application of deep learning, where if you in a first glance this looks like some kind of script for a play. If you start reading, alas, I think ye shall become approached, and the day when little Saran would be attained into being never fed, and who is but a chain and subjects of his death, I should not sleep. So when you look at the text, this seems like that it has managed to be in proper structure, but it doesn't really make sense. Okay, so this play that you're looking at was generated by a deep learning architecture or deep learning algorithm. The key achievement here is that the deep learning algorithm learn to write plays, at least figured out what words to use, in general what structure it should be. The good meaning plays, or we are very far from movie scripts being written by AIs, but we are reaching there, and this is a huge achievement. This is another fun example. Do you notice what's happening here? Somebody is writing only a word, and deep learning algorithm is writing a deep learning code. This is much more than a simple autocomplete. In autocomplete, rather where when you hit tab and in scikit-learn you were suggested or rather shown all the functions available and you selected one. This is not that. It tells you what code makes sense. As in when you're writing more and more lines of code, it tells you what line of code to write. And that is again a huge achievement. Of course, we are very far from where we can sit back and relax and all the deep learning development is done by the deep learning algorithms themselves, but we are making good strides towards that. In general, in our course, we'll be talking about 4 broad levels of algorithms that pretty much covers all of these and more use cases that we will come across. The first set of detail that we'll go into is looking at simple neural networks with many layers added in between, which are called feed-forward networks. Then we'll move towards special architectures like convolution networks which work with images and videos. We'll look at recurrent neural networks and its variations, RNN, LSTM. These sequence specific architectures work very well with text data, audio data, time series data. We'll be looking at some very interesting unsupervised algorithms as well, where we are not really trying to predict as such something, but very interesting use cases we will find in GANs and autoencoders and off-field networks. This was simple neural network that we have seen earlier, that logistic regression is nothing but neural networks without a hidden layer, and that gives a linear rather can separate a linearly separable set of observations. As and when the structure of the problem becomes more and more complex, we can keep on adding hidden layers to extract that pattern from the data. Okay, and these feed-forward neural networks generally you'll find can be used with the tabular data, the traditional data that we are feeding into machine learning algorithm. As we start with more unstructured type of data such as images, a specific kind of architectures come into place, and it doesn't look the way a feed-forward network looks like. But don't worry about these figures yet. We have hours of detailed discussions on these algorithms. I'm just giving you an overview of what all kind of algorithms we'll be talking about. Okay, so convolution neural networks essentially are a specific architecture which preserves or makes use of the positional information in images and videos and so on, and makes use of that to give us better classifiers, better predictions. Then there are recurrent neural networks which make use of sequential information preserved in the data, such as text or audio and time series. And it has found many amazing use cases such as translation or generating text or forecasting without any assumptions in time series. If you recall ARIMA models, there were tons of assumptions involved. None of those really matter here, and these models can not only extract short-term dependency but long-term dependencies as well in any kind of sequence, not just numerical time series data. Okay. Then as Hopfield network is without again going into details, this is one of the algorithms which we will see an example of for restoration of images given the blurred part, and bringing them back to the enhanced version. Autoencoders are again a very good use case on the unsupervised learning part. So autoencoders, you can say the nonlinear PCAs, to simplify that. It can help bring down the dimension of the data drastically, and it can make use of nonlinear relationship between variables, which enables it to bring down the dimensions to a crazy amount of lower numbers. Generative adversarial networks is a very new algorithm, and it's being talked about a lot. Is something which can be used to generate data. All the images that you see on the slide of seemingly look like bedrooms. These are not real pictures. They were generated by generative adversarial networks. First they were fed lot of images which were of bedrooms. Now once they've gone through it, if you ask them to generate a new image of a hotel room or bedrooms, they do generate that. Although if you look closely, many of the rooms are weird. I mean, some are full of just pillows or just beds or some weird combinations. But imagine that these almost looking like hotel rooms images were randomly generated, each pixel at a time, by a neural network algorithm. This has tons of different use cases which we'll go through in the course. And these are again broad level algorithm that we discussed. We'll be discussing many more use cases and slight variations of these algorithms. Majority deep learning teams make use of many tools such as TensorFlow or PyTorch, and then deep learning Java based framework CNTK coming from Microsoft, MXNet, and so on. We will be picking up TensorFlow as the base library, which is pretty popular, and there are a lot of research and a lot of applications that you'll find in TensorFlow. We'll be using Keras as something which is a top level library on top of TensorFlow, which makes your life easy in terms of coding what we need to write, maybe 30 lines of codes in TensorFlow, we can achieve that in Keras maybe in 3 lines. So first we'll learn the basics of TensorFlow and then we'll move on towards Keras. If you want to work on any other of these tools, you can. We will provide you resources to do it, but we will not be talking about officially in the course, in the live sessions. And reason being that, okay, there is no end to how many tools we can discuss that, but we don't want to replicate what we are trying to implement. We'll rather focus on one tool which has more adaptation in the industry. On the hardware size, no, when we start deep learning, that doesn't mean now you need to buy machines with GPUs. That's not the case. We'll start with simple, in your machine deep learning algorithms, just that it might take longer, or we might be forced to work with a small amount of data. We will, however, see how to set up GPU instances on cloud. There are multiple options. We will be making use of Google Cloud Platform because it gives you $300 credit to start with, and that is more than enough to learn deep learning and keep on doing this for 2-3 months, given that you carefully switch off your instance whenever you're not using it. And there are other options, AWS, Microsoft Azure, and there are tons of other providers as well. Again, we will provide you with resources. We will handhold you if you want to use any of the other options, but we will not be officially covering them in the class. Okay. In the next video, we will look at underlying optimization algorithm, starting with gradient descent. We are already aware of gradient descent from the previous machine learning course. We'll be looking at some variants of gradient descent, stochastic gradient descent, stochastic gradient descent with momentum, RMS prop, Adam optimizer. We will be talking about that in the next video. See you there.